a little bit puzzled because I'm going to present a more theoretical paper. So it is up to the organizers to decide whether I'm in the correct track right now. And with that, let's start the presentation. So my work is on fitness landscape analysis on binary dynamic optimization problems. That sounds a little bit theoretical and freaky, I know, but there is good reason why I do this. Industry 4.0 and the digitalization in the production area brought with it the understanding that most optimization problems are inherently dynamic. They change over time, and the algorithms that optimize these problems have to cope with that. And although there is very little literature on this part, the biggest influence from an optimizer perspective is the optimizer itself, usually, because dependent on your optimization, you take a decision that impacts the future state of your optimization problem. The target, of course, with all the Industry 4.0 and prescriptive artificial intelligence idea is to have open-ended optimization algorithms and modeling algorithms that work with minimal supervision essentially forever doing their tasks. Here is an artist rendition when this no longer works, because here we see, let's say, an abstraction of the stacking warehouse where the optimizer locked itself out of any possible moves it can do. Every stack here has reached maximum height. And this was done in a previous work that we presented on a conference this summer. And for this conference, I wanted to take a step back into the theoretical work and work out ways to find state deteriorations and to analyze problem algorithm states for dynamic optimization problems on a more grounded theoretical level. What can we do to detect when the state of the dynamic optimization problem underneath the optimization algorithm changes? There is a go-to method to analyzing problems, and that is fitness landscape analysis. That is usually 90% of the time done on static optimization problems and involves capturing the problem in statistical features like an autocorrelation value, an information content value, and the size of neutral areas in the problem. What you're essentially doing is you're starting a random walk on your problem and then calculating, okay, how rugged is my optimization problem? Is it flat everywhere? Do I have large areas where different solutions to my optimization problem give all the same quality? There is a small amount of literature corpus for statistically analyzing dynamic fitness landscapes. Yeah, literature on this is very sparse. There are about maybe half a dozen papers on that in the last 10 years, which I find very regrettable, because this is something that is actually pretty important for if we want to go forward with the Industry 4.0 trend. We need to have a better understanding of the systems that we're dealing with in a way that the algorithm automatically can measure them. Because you can, of course, track your optimization problem by designing domain-specific features, like, for example, for the stacking problem, how many out-of-order relations do I have for any block, or how many blocks are overdue. But it would be nice to have a more black box approach so that the algorithm has some chance of tracking, okay, my problem has significantly changed from when I started. Maybe I'm deteriorating. Maybe I need to reparameterize. And today I will just show you the results of applying standard fitness landscape techniques to two dynamic optimization problems with time linkage, with the property that the decisions that the optimizer make actually influence the problem, which is sadly not that common in current literature. First problem, very, very easy. Just to lay out the ground rule is a dynamic and time-linked variation of the classic one-max problem for binary optimization, where you have a target state that is always fixed, a world state that you want to have as close to the target state as possible, and you have the solution of the algorithm that you want to have as close to the world state as possible. And now you have random changes in the world state, and you have to introduce the time linkage, the probability that the world state simply takes the value that is given by the solution. So you can, if you repeatedly submit solutions as decisions that move the world state towards target state, you have both a short-term gain and a long-term gain. It's a very, very simple problem, can be solved with a local search. Is fully separable, but it displays the very basic ideas of, okay, I have random influences, I have optimizer-made influences, and I need to solve this problem not once, but essentially for eternity. The second problem is actually, I think, a little closer to reality, and is a dynamic multidimensional backpacking problem, where you can essentially think of your rows in this matrix as different actions you can take, and these actions cost you resources and yield a certain profit. Of all types of resources, you have to stay beneath a certain capacity, and you want to maximize profit. Problem here is that you have to do this essentially forever, and there are stochastic processes that change the profits of any action, and that change both the resource capacities and demands for any action. And now we introduce time linkage and include the simplest of essentially stock market simulation, and think of unpicked items or actions as increasing demand, and so you increase the profit, and the second you pick an item or an action, it decreases in profit. And so you see how this system can deteriorate just as the stacking problem in the intro did, because you can just never pick a certain action, drive its value essentially either to a set maximum or to infinity, and then pick it. So there are some very clever things that you can do when solving this problem, but that's not why we're here right now. I want to analyze the established and standard FLR measures on these problems to get a ground feeling how these problems behave under different algorithms. And I could use a self-adaptive evolutionary strategy or a very complex multi-population genetic algorithm for that, but that would essentially just poison my analysis results. So I'm doing the analysis on very, very simple algorithms, namely a local search that tries to maximize the short-term gain in any situation, an inverted local search that is my stand-in for a bad algorithm effectively, and tries to essentially minimize the short-term search, and in spirit with the no free lunch theorem, maybe the problem is dynamic enough that random guessing is the best thing we do. And for the dynamic one-max problem, because this is so simple, it is actually possible to design an oracle algorithm that optimizes purely for the long-term game. On the side here, we see a small diagram that compares the degree of intrinsic and of intrinsic dynamicity, let's say how strong the time linkage is, with the performance of these three algorithms. And we see that there is essentially a clear cutoff at which point the time linkage is strong enough that it is suitable to always optimize for long-term gain. If this time linkage is weaker, especially when compared with the inherent random stochastic changes in the dynamic problem, it is better to be greedy and optimize for short-term gain. So just to set the playing field a little bit here. So, and then let's jump right into the results here and look at first the autocorrelation value, which is for any given point in time, how rugged is the current optimization problem right now? How non-neutral, how informative is it? And we see something that I both enjoy, on the other hand, dread, is that for the first 11 pictures where we see the various bin packing instances, that there are significant differences in the problem state when you apply different algorithms. That is nice, except for when you look at the 1max problem, you see that the ruggedness does nothing. It doesn't change irrespective of the algorithm applied to it. Also, we see the changes are all significant, at least according to pairwise testing. I think one-way ANOVA I used here, but the effect of these changes of the algorithm on the autocorrelation is very, very small, which is first okay. What's that mean? On a larger scale, it allows us to still differentiate between different problem instances. So we can use autocorrelation, at least that's the working theory, to do algorithm parameterization later down the line. I'm not presenting that right here. On the other hand, let's look at one select example from the dynamic fitness landscape analysis, and we see something interesting, namely that the effects of the algorithm on the dynamic change are almost indetectable for most of the multiple knapsack problems. Keep that in mind when we walk to the next slide. For the 1max problem, we see it that the application of different algorithms has a strong influence on the dynamicity of the problem. Okay, so far, so good. Now we can construct distance measures for the intrinsic problem states to see how much the problem actually changes and how much, I'm sorry, I have a typo up there. How much the problem actually changes and how much that correlates to what we have measured before. And here we see something actually pretty sobering, namely that algorithms that try to achieve the best or the worst possible solution introduce actually pretty significant changes within the problem state. We have huge variations between these change severities. Some of them are actually, since this is a logarithmic scale, actually pretty significant. You can drive these item or action prices really up if you want to, but the dynamic fitness landscape analysis does barely reflect these changes. So we have the very dicey problem that the dynamic optimization problem deteriorates and creates significant changes underneath the surface, of which the algorithm, since it's usually a black box optimization algorithm, is not informed. Yeah. Coming to a close, applying fitness landscape analysis on dynamic optimization problems is difficult, to say the least, and there is much work to be done. The choice of the algorithm hugely impacts the problem state progression, which is usual for time-linked dynamic optimization problems, but this is not always reflected on the fitness landscape analysis measures. So we kind of need to have better measures. Also, the effectiveness of these measures is hugely dependent on the problem, which is consistent to all the experiments I did on actual real-world optimization problems. Yeah. Time linkage as a property of optimization problems is somewhat underrepresented in the black box optimization literature, which makes this little excursus hopefully worthwhile for your time. And of course, it's a simple lesson learned, but I would like to remind everyone who is doing this that a degree of dynamicity severely impacts which strategy is actually optimal and which static optimization goal you should pursue when working on the dynamic problem. And with this, thank you for your time.
Okay, thank you, Bernhard. You are perfect in time. So, there are any questions from the audience? Not really dead, but if you want to take a question, you can say. I think there are no questions. I have one for you. Can you give us your vision about the potential implication, applicability of this kind of analysis on real cases? Just for example, if I have an industrial problem, scheduling problem, for example, no? In which way the decision maker can be helped by using this kind of analysis?
Yeah, well, the very first and simplest application of these types of analysis is essentially to pull the emergency brake when the problem algorithm state deteriorates. When you can classify your current state as very anomalous, you have to involve a human decision maker rather now than later. And if you track, let's say, ruggedness or neutral areas on your problem, and you see for some very weird reason my problem just became completely neutral and whatever I'm doing right now has no impact more, then you need to get the human involved stat. On the other hand, you could do more intricate things like, okay, my problem is gradually becoming more difficult, so I need to reparameterize my algorithms, or I need to use a different algorithm altogether.
Okay, and do you think? Probably there is a question. Eugenio Rocha, please.
Yeah, thank you. This idea is very nice. In continuing the question that Salvatore made, let me ask you if it's possible, if you think it's possible to apply the fitness landscape analysis in a dynamical way for machine learning in deploy. Let me explain. Usually people, what they do is I'm going to talk about applying some classifiers and so on, and you have the models, you do the hyperparameters, so the model is very nice and working. Then you put that in a factory and it is deployed. But after some time, because all the manufacturing line has a lot of variabilities and the historical data maybe is not representative, we need to retrain the models. So there is a state deterioration because the model, the machine learning model is not doing with the metrics that you decide, not doing the job that you want to do. So somehow can we use this method to derive when a threshold, a dynamic threshold to decide when to do again the training of machine learning models, for example?
Well,
what do you think?
There are two things you can do. If I understood you correctly, you are viewing the problem of setting the hyperparameters of the model as your optimization problem.
Right.
And you could apply fitness landscape analysis to this essentially meta optimization problem where you want to find your hyperparameters. And if the
performance of the machine learning is deteriorating with respect to the world, because there are random information happening, because the data is changing and the response of the predictive algorithm is changing, and we can measure how good it is.
Yes.
Okay, we have some kind of oracle after some time,
Yeah, and you can, I think in this particular case, you can even combine the best of both worlds. You can combine the numerical features of your hyperparameter fitness landscape with semi-domain specific features, like say some statistical features you generate over your data set to detect when things essentially get out of hand. So you can actually use both the fitness landscape analysis measures and the original machine learning features to track when things start to cook. So I think that's a very good idea. I am fully honest with you. I don't know how much more potent the fitness landscape analysis measures will be compared to features that you simply calculate out of the original data set, because there is simply more information in a strict sense in there. But possibly it would be useful to detect whenever your hyperparameter optimizer starts to get on thin ice. I think this is actually pretty powerful, what you're talking about now.